Now, sources of power for the active galaxies. All of this depends on the presence of a supermassive black hole at the center. Its gravitational pull provides the energy that produces all the rest of this. Immediately surrounding the black hole, we have a cloud of gas called the accretion disk. Accretion disk meaning it's sticking onto the black hole, falling into it. The accretion disk is flattened out pancake-like, or could be kind of puffed up in the middle, where some of them are different. But it's a disk of gas, almost whirlpool-like, flattened out at least along the edges. And it's swirling into the black hole. Now, the inner parts of the disk, closest to the black hole, are orbiting around the black hole most quickly. The farther parts away from the black hole are orbiting more slowly because the force of gravity is weaker there. Now, this is the same as what happens in our own solar system, where Mercury, the closest planet to the Sun, orbits the most quickly, and Pluto, which is farthest or much farther from the Sun, goes around a lot more slowly. But in our solar system, there's all this empty space between the planets, and so they don't bump into each other. But in the accretion disk, it's one continuous cloud of gas. So all the gas molecules are rubbing up against each other, and the inner parts of the accretion disk, going very quickly, rub up against the outer parts moving slowly, and they heat up from friction and glow. And they glow not just red hot, they glow white hot, even ultraviolet hot. Now, this is what we call differential rotation, meaning that the different parts of the disk rotate at different speeds, and the differential rotation is the key for producing light in the accretion disk. If you have different speeds, you have this friction that builds up, and that produces heat, and that produces light. So the accretion disk produces light in the visible and the ultraviolet regions of the spectrum, mostly. And the temperature is hottest around the inner part of the disk in a ring around the black hole because the differences in speeds are highest there. As you get to the outer parts of the disk farther from it, then the differences in speeds are much lower and you have a cooler temperature and a much redder look to it. So the inner parts have a very hot blue light and the outer parts have a cooler and redder light. Okay, so thermal radiation from the accretion disk, it's black body emission, and it's a continuum. Surrounding in a ring around the accretion disk, you have the so-called dusty torus, T-O-R-U-S, which is just a technical term for a donut shape. This dust ring, probably lined up with the accretion disk, absorbs light from the accretion disk that shines, well, at least the light that shines sideways. And because it's dusty and it's more or less opaque to light, it absorbs that light and it heats up the dust and it re-emits it as infrared light. The dust is warm and glowing in the infrared. So the accretion disk produces ultraviolet and visible. The torus produces infrared light. Okay, now, surrounding, orbiting in all different directions outside the accretion disk, you have clouds of gas, a lot like nebulas inside the galaxy. And these clouds are, as they go around the orbit around the black hole, at times they're exposed to the ultraviolet light from the accretion disk. When this happens, they absorb some of the photons coming off and you get fluorescence in the clouds. They absorb some of that light, like the ultraviolet. The electrons get excited, they jump up a few orbitals, and then when they fall back down, they emit their characteristic emission lines. The chemical spectrum of that gas. But because some of these gas clouds are orbiting, moving towards us, and others are moving away from us, you get blue shifting of those emission lines from the ones moving towards us. You get red shifting from those moving away from us, and this just blends, all those lines get blended together. The red shifted and the blue shifted versions of each line are blended together, making a very broad, wide emission line. In fact, every emission line coming out of those clouds will be broadened by the Doppler shifting. In fact, the more massive the black hole is, the faster these clouds move and the more they're Doppler shifted and the broader the lines get. So these broad lines turn out to be very characteristic of active galaxies, and we can measure the width of the line, and that can tell us how massive the black hole is. These become really good ways of measuring black hole mass. So these are called the broad line clouds. You also can have some clouds that are orbiting much farther from the black hole, and because they're farther away, they're moving more slowly, and there's less Doppler shifting. These are called narrow line clouds because they're not Doppler broadened as much. And we can notice sometimes that the emission lines from quasars and from other AGN show a broad line part to each line, and sometimes a narrow line part to that line as well. And so we know that there are clouds in both places. If the clouds weren't moving, they would be very, very narrow lines, which is in fact what we see in regular nebulas inside the Milky Way. Now, maybe the most mysterious part of active galaxies are the jets. Jets are, well, they're jets of plasma shooting out from the north and south poles surrounding the black hole. And we still have a lot to learn about these. They are collimated, meaning they are beamed in narrow lines. Generally two jets, and we think that the plasma, because it's ionized, electrically charged gas, is being funneled along the magnetic fields coming off the north and south poles of the black hole. It's not gas that's coming out of the black hole, but from the accretion disk surrounding it, or maybe a hot halo surrounding the accretion disk. We don't quite know how the jets are fueled yet. We're still trying to study this. So because charged particles don't like to move across magnetic field lines, they like to move along them, then the electrical charges spiral along these magnetic field lines, and whenever you get a spiraling electric charge, you get what's called synchrotron radiation, named after the synchrotron particle accelerators, where they discovered this in. And these charged particles, like electrons mostly, will emit light in the direction they're moving, and not in other directions. So you get sort of like flashlight beams, searchlight beams shining along the direction of the jet and not any other direction. So you get two beams of light, one coming out of the North Pole, one coming out of the South Pole, and the jets go off for sometimes millions of light years, certainly thousands of light years, way off beyond the galaxy and into deep space. And this provides some really spectacular images in the radio. Okay, now the synchrotron radiation largely produces radio waves, but it can continue on up into shorter wavelength light and higher energies as well. In fact, you can get extremely high energy light, X-rays and gamma rays, out of these jets. Now, normally we'd call these synchrotron jets, or really just radio jets, but you can get this much higher energy radiation, and we think that this is from the Compton process, where the electrons in the jet moving at near light speed bounce off of photons that have already been emitted, like from the accretion disk possibly, maybe from the synchrotron radiation in the jet, and the electrons can give off some of their kinetic energy to the photon. Well, the photon can't speed up. It has to move at the speed of light. But you give it extra energy, and it goes to a shorter wavelength or higher energy. So you can boost a visible light or an ultraviolet light photon up to gamma ray, X-rays, or even gamma rays. And so if you're looking along the beam down into the jet, you can see these higher energy photons then. And this is a feature especially of what we call blazars, which we'll get to later.